This video shows how we tell if space objects are moving toward us or away. The trick is redshift. Light stretches as it travels, and stretched light looks redder. Think of light as a wave. Short waves, more blue. Long waves, more red. If the color changes, the wavelength changed. So, does the speed of light change too? No. In a vacuum, light always moves at the same speed. See. What changes is frequency and energy. Longer wave, lower energy per photon. Shorter wave, higher energy. So, why does the wave stretch? There are 3 ways to get the same effect. Doppler. If a source recedes, the wave stretches, like a siren passing by, but with light. Cosmological. Space itself expands, and that expansion stretches the light as it travels. That's how we study the distant universe. Gravitational. Climbing out of strong gravity, light loses energy and shifts to red, like escaping a deep well. How do we measure this for real? We don't chase single photons. We collect many and split them by color. A spectrum. In that spectrum we see lines, dips or spikes at very precise colors. They're chemical fingerprints. Hydrogen leaves a famous one in deep red, H-alpha. We know each line's rest position from the lab. Then we observe a galaxy, measure where those lines fall, and compare. If they're at longer wavelength, more nanometers, we've got redshift. We summarize it with a single number, z. So, do all lines shift by the same amount? They shift by the same fraction, not the same number of nanometers. If z is, say, 0.152, every wavelength is multiplied by 1 plus z. Bluer lines move a few nanometers. Redder lines move more nanometers. But the factor is the same across the whole barcode. What about dust making things look red? Great point. Dust removes more blue light so objects look redder. But dust doesn't move the lines. Redshift moves the entire pattern. That's why we trust lines, not color by eye. Why does this matter? Nearby, z tells us if something approaches or recedes. Far away, z tells us how much the universe has expanded since that light left. In extreme zones, z reveals the pull of gravity. So we read the cosmos like a barcode, find a known fingerprint, measure how far it shifted. With that one number, z, we recover motion, distance, and time. And yes, the same logic powers radial-velocity searches for exoplanets. Tiny stellar wobbles betray hidden worlds. But that's a story for the next video.